October 16th. One photograph. And the universe may have just blinked back at us. From the darkness between the stars, a single image of 3I Atlas, captured by a telescope in Spain, has shattered the rules. The evidence isn't buried in data, it's staring us in the face. A jet, erupting from the front of the interstellar visitor, driving straight toward the sun, not from its tail, not from melting ice, from the one place no comet should ever breathe. And here's the part that chills me. Weeks earlier, NASA had a chance to show us this, and their cameras went dark. Coincidence or deliberate silence? Stay with me tonight, because by the end, you'll see why this image may be the proof we've been waiting for. If these revelations have you on edge the way they have me, don't just watch from the sidelines. Hit like and subscribe right now, because you don't want to miss anything as this unfolds in real time. Tell me in the comments where you're watching from, what time it is there, and whether you think we're actually being told the truth about these discoveries, or they are trying to bury the real story. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Part 1. The Sunward Jet Revelation. On October 16th, 2025, Avi Loeb published an image that shouldn't exist. The photograph came from the 2-meter twin telescope in Arizona, a modest instrument compared to the giants like Hubble or Webb, but sometimes the most important discoveries don't come from the most expensive equipment. They come from looking at the right place at the right time with eyes willing to see what others dismiss. The image shows Comet 3I Atlas, an interstellar visitor that entered our solar system earlier this year. Except here's the problem. The image reveals something extending from the comet's nucleus, a jet-like structure approximately 6,000 kilometers long, and it points directly toward the sun. You might think this sounds unremarkable until you understand one fundamental rule about comets that has held true for literally every comet ever observed in human history. They always eject material away from the sun, never toward it. Solar radiation pushes comet tails outward like wind filling a sail. The solar wind, that constant stream of charged particles flowing from our star, sweeps dust and gas away from the sun's direction. This is Physics 101, the kind of thing textbooks use as a simple example of how radiation pressure works. Comets can have multiple tails, dust tails and ion tails, but they all point away from the sun, always, without exception. Until now. Loeb and his team stacked 159 separate exposures to create this image. The signal is faint, barely visible against the background noise of space, but it persists across multiple frames. This isn't a single glitch or a cosmic ray hit. The structure appears consistently, exposure after exposure, a ghostly plume extending sunward from a chunk of ice and rock that by all rights should be doing the exact opposite. Some scientists immediately called it a processing artifact, the kind of false signal that can emerge when you combine multiple images. Others suggested it might be an anti-tail, a well-documented optical illusion where dust particles along a comet's orbit can appear to point toward the sun from certain viewing angles. Here's why that explanation doesn't work. Anti-tails are geometrical illusions. They're not real structures but perspective effects, like how railroad tracks appear to converge in the distance. They disappear when you change your viewing angle or wait for the comet to move along its orbit. The feature in the 3I Atlas images doesn't behave this way. It remains consistent across observations from different times and positions. Loeb calls this the weirdest evidence yet of non-natural origin. Those are strong words from a Harvard astronomer who has spent decades studying black holes and cosmic phenomena. The psychological impact of seeing something like this cannot be overstated. We've had hints before, strange acceleration patterns in Oumuamua's trajectory that couldn't quite be explained by outgassing spectroscopic data showing unusual chemical compositions. But this is different. This is visible. This is a structure you can point to in an image and say, there, look at that. Explain that to me using conventional comet physics. Oumuamua accelerated as it left our solar system in 2017, speeding up in a way that suggested some force was pushing it. Scientists proposed various explanations, outgassing from sublimating ice, even though no outgassing was detected. A tumbling motion that could create thrust, even though the tumbling pattern didn't quite match. Or Loeb's controversial suggestion that it might be a light sail, a thin reflective surface pushed by solar radiation. Every explanation had problems. Every explanation required stretching our models just a bit beyond their comfortable limits. With 3i Atlas, we're not inferring propulsion from velocity changes. We're looking at what appears to be an active plume pointing in the wrong direction. If this jet is real, if it's truly ejecting material toward the sun, then something is producing thrust. Something is pushing against the comet's natural motion in a way that defies every model we have for how these objects behave. Imagine you're watching a river flow downstream, and suddenly you notice one stream of water flowing uphill. Not meandering or eddying, but actively climbing against gravity. That's essentially what we're seeing here. The question isn't whether this is interesting. The question is whether we're brave enough to follow this observation to its logical conclusion, even if that conclusion makes us uncomfortable. What if this jet is real? What if it's not a comet at all? What if we're watching something that only looks like a comet, because that's what we expect to see when we look up? And here's the truly unsettling part. If this image from a 2-meter telescope in Arizona shows this anomaly so clearly, what did the instruments that got much closer see? Part 2. The Catalogue of Anomalies Revisited. Every mystery starts with a single clue, but sometimes a mystery doesn't reveal itself until you lay all the clues out on the table and realize they form a pattern. 3i Atlas has been giving us clues since it was first detected, and each one individually could be dismissed, explained away, filed under interesting but inconclusive. Taken together, they start to look less like a collection of oddities, and more like a fingerprint that doesn't match anything in our database. Let's start with the nickel. Spectroscopic observations of 3i Atlas revealed a gas plume unusually rich in nickel, an element that shouldn't be prominent in comet emissions. Comets are dirty snowballs, mixtures of water ice, dust and various frozen volatiles like carbon dioxide and methane. When they approach the sun and heat up, these materials sublimate, turning directly from solid to gas. The resulting spectrum should show water, carbon compounds, maybe some sodium. Nickel is not on the standard menu. The counterargument goes like this. Maybe this comet formed in a nickel-rich region of its home star system. Maybe it incorporated unusual amounts of metallic dust during formation. Possible? Sure. Unusual? Definitely. Then there's the water problem. Comets are supposed to be icy objects. Water makes up a substantial fraction of their composition. 3i Atlas shows a surprisingly low water fraction compared to typical comets. Again, you can construct explanations. Maybe it formed farther from its star where water ice couldn't condense efficiently. Maybe it lost water during a previous close stellar encounter. Each explanation requires invoking special circumstances, but okay, space is big and weird. Special circumstances happen. The polarization measurements add another layer of strangeness. Light reflecting off 3i Atlas shows extreme negative polarization, meaning the electric field oscillations of the reflected light waves are oriented in a way that's rare among solar system objects. Most comets and asteroids show positive polarization or modest negative values. This object pushes into territory occupied by only the most peculiar bodies we've studied. Scientists note this, add it to the data, and move on because what else can you do with a single weird measurement? Here's where it gets interesting. The trajectory of 3i Atlas through our solar system follows a path remarkably close to the ecliptic plane, the flat disk where Earth and most planets orbit. Interstellar objects can come from any direction in three-dimensional space. The odds of one arriving nearly within our solar system's plane purely by chance are small, not impossible, but small. And the direction it came from. That region of sky includes the coordinates from which the famous WOW signal was detected in 1977, a powerful radio burst that remains unexplained to this day. Any one of these anomalies deserves a footnote in a paper. 2 anomalies might raise eyebrows. When you get to 4, 5, 6 unusual properties, all manifesting in the same object, you start to wonder whether you're looking at a series of unlikely coincidences or whether something more fundamental is wrong with your assumptions. This is the argument Loeb has been making, not just about 3i Atlas, but about Oumuamua before it. Science resists alien explanations because that's not how science works. You don't jump to the most extraordinary conclusion when ordinary explanations might suffice. But what happens when ordinary explanations keep failing to account for the observations? Oumuamua gave us an elongated shape, either a cigar or a pancake depending on which analysis you trust, Unlike any asteroid or comet previously observed, it gave us unexplained acceleration. It gave us no detectable outgassing to explain that acceleration. It gave us a trajectory that suggested it had been travelling through interstellar space for millions of years. Each anomaly got its own creative explanation, and the scientific community moved on because Oumuamua was already leaving, receding into the darkness beyond Neptune's orbit, and there was nothing more we could do. Now we have 3I Atlas. Now we have another interstellar visitor displaying behaviour that doesn't fit our models. The press coverage has been muted, careful, hedged with qualifications and alternative explanations. Institutional science moves slowly, and that's usually a good thing. You don't want astronomers announcing alien spacecraft every time they see something unusual, but you also don't want the weight of institutional caution to blind us to genuine anomalies that might be trying to tell us something important. Independent telescopes and amateur astronomers have been crucial in tracking 3I Atlas. They don't have institutional review boards or funding agencies to worry about. They point their instruments at interesting objects and share what they find. The October 16th image came from this community of independent observers, people who are motivated by curiosity rather than career advancement. Sometimes that freedom allows you to see what others won't. The jet pointing toward the sun adds weight to the catalogue of anomalies because it's not a spectroscopic quirk or a statistical oddity. It's a visible structure that appears to show propulsion, active thrust in a direction that natural comet progresses cannot explain. You can't dismiss this as a measurement error or an unusual but plausible composition. This is behaviour, and behaviour implies agency, or at least physical processes we don't understand. Which brings us to a question that keeps getting louder the more data we collect. What did the spacecraft that flew past Mars see? Part 3. The Mars Flyby Silence. In early October 2025, 3I Atlas made a close pass by Mars, coming within observational range of multiple instruments orbiting the red planet and even within potential view of rovers on the surface. This was the observation opportunity of the decade, a chance to study an interstellar object with equipment specifically designed to analyse celestial bodies up close. We have the European Space Agency's ExoMars Trace Gas Orbiter, a spacecraft equipped with high-resolution cameras and spectrometers. We have NASA's Mars Reconnaissance Orbiter with its powerful telescopes. We have rovers on the surface, including Perseverance, which could potentially image the comet during the flyby. The official releases from these observations have been remarkably bland. Some images were shared showing 3I Atlas as a faint smudge against the background stars. The press releases described the observations in technical terms, noting the comet's brightness and approximate size. What they didn't mention were anomalies. No discussion of unusual jets, no commentary on strange spectroscopic features, just routine observations of a passing comet. Move along, nothing to see here. This silence is deafening when you consider the context. The 2-meter twin telescope in Arizona, observing from Earth hundreds of millions of kilometers away, captured images showing a sunward jet. Mars-based instruments, orders of magnitude closer with presumably better resolution and viewing angles, released images showing nothing unusual. Either the jet wasn't visible during the Mars flyby, which would be strange given its apparent persistence, or the organizations controlling those instruments decided not to highlight what they saw. Mars provides a unique vantage point. Earth-based telescopes look at 3I Atlas through our atmosphere, through light pollution, through the geometric constraints of our single position in space. Mars sees it from a completely different angle, with instruments above any atmospheric interference, with the ability to track the comet continuously without day-night cycles interrupting observations. If the sunward jet is a real physical structure, the Mars instruments should have seen it weeks before the Arizona telescope did. So where are those images? Speculation spreads quickly in the absence of official information. Some researchers privately wonder whether the Mars data showed anomalies that were considered too sensitive to release. High-resolution datasets exist but haven't been made publicly available, which isn't unusual in itself. Space agencies often delay full data releases until papers are published or analyses are complete. But the timing feels suspicious. The most dramatic images of an interstellar object ever captured, and we get carefully curated selections that show nothing remarkable. History provides uncomfortable parallels. Lunar data was sometimes delayed or sanitized during the Apollo era, not always for nefarious reasons, but often because organizations wanted to control the narrative or avoid premature speculation. The same pattern appears in other contexts. Interesting observations get held back while explanations are developed, and by the time information reaches the public, it's been processed through layers of institutional caution. Scientific papers published so far from the Mars observations stick to dry descriptions of orbital mechanics and photometric measurements. Nobody mentions propulsion. Nobody discusses the possibility that this might not be a natural object. The papers read like routine comet studies because that's what they're required to be. Peer review doesn't reward speculation, and careers aren't built on controversial claims that can't be definitively proven. Meanwhile, online communities of amateur astronomers claim to have detected signal anomalies during the Mars flyby. Radio observations showed brief increases in the electromagnetic emissions that don't match typical comet behavior. These reports are unverified, often coming from hobbyists with equipment that isn't calibrated to research standards. Mainstream science ignores them, and maybe that's appropriate. Or maybe dismissing amateur observations is exactly how you miss crucial data that doesn't fit your expectations. The institutional silence around the Mars flyby becomes more interesting when you realize what happened next. Less than a month after 3I Atlas passed Mars, NASA's Psyche probe, which was in a position to potentially observe the comet, went dark. Part 4. The Psyche probe blackout. The Psyche mission launched in October 2023 with a straightforward objective: travel to asteroid 16 Psyche, a massive metallic body in the asteroid belt that might be the exposed core of a protoplanet. The spacecraft carries cameras, spectrometers, and magnetometers designed to study a world unlike any we've visited before. It's a science mission, not particularly glamorous compared to Mars rovers or outer planet probes, but important for understanding planetary formation. In September 2025, Psyche's public imaging feed went silent. NASA's explanation cited calibration procedures and bandwidth management. Deep space communication is expensive in terms of both power and time. Spacecraft can't transmit constantly, and when they do, mission controllers prioritize science data over public outreach images. Sometimes feeds get interrupted for weeks during critical operations. This is normal. This is how space missions work. Except the timing is remarkably convenient. Psyche's trajectory through the inner solar system placed it in a position where its instruments could have captured observations of 3I Atlas during the comet's approach. Not a dedicated observation, perhaps, but certainly within the range of opportunity targets that spacecraft sometimes image when their primary objectives allow. The imaging feed cut precisely when those observations would have been most valuable. Weeks after the blackout began, the United States federal government entered one of its periodic shutdowns due to budget negotiations. NASA's public affairs offices reduced operations. Press releases slowed. The usual channels for public scrutiny became harder to navigate as civil servants were furloughed and websites updated less frequently. If you wanted to bury information or simply avoid questions about sensitive observations, a government shutdown provides excellent cover, not through active conspiracy, but through bureaucratic paralysis. Parallels exist in recent space history. The International Space Station has experienced moments where live feeds mysteriously cut during events that UFO enthusiasts claimed showed anomalous objects. NASA's explanation always involved technical issues or routine switching between cameras, and those explanations were probably true most of the time, but the pattern creates suspicion. Important moment approaches, feed cuts, official. Explanation involves technical difficulties, skeptics remain skeptical. Loeb suggested that institutional reluctance to admit anomalies runs deeper than simple scientific caution. Organizations like NASA exist in a complex political environment where funding depends on congressional approval, where missions are justified by public support, where anything controversial can become a budgetary weapon. Announcing that an interstellar object might be artificial would trigger an enormous response, potentially overwhelming the agency's ability to control the narrative or conduct careful analysis. Silence becomes the safest option, at least until you're absolutely certain of what you're dealing with. Critics of this conspiratorial framing argue that nothing unusual is happening. Space missions have technical issues. Data takes time to process. Scientists need to analyze results before making public statements. The appearance of secrecy might simply reflect normal operational procedures being viewed through a lens of suspicion. Most spacecraft anomalies have boring explanations. Most mysteries resolve into mundane technical problems or misunderstood data. But here's what makes the Psyche blackout unsettling in context. You have an interstellar object displaying multiple anomalies. You have Mars observations that showed nothing unusual despite better viewing conditions than Earth. You have a spacecraft that could have provided another perspective going silent at the crucial moment. You have a government shutdown making public scrutiny more difficult. Each element alone means nothing. Together, they form a pattern that feels less like coincidence and more like orchestrated avoidance. The broader question isn't whether NASA deliberately hid evidence. The question is whether institutional structures make it easier to ignore uncomfortable data than to confront it. Organizations optimize for stability. Rocking the boat threatens funding, careers, and comfortable assumptions about how the universe works. If you're a mission scientist and you see something anomalous in Psyche's data, do you immediately publish and risk ridicule, or do you quietly shelve it for further study that might never come? The system rewards caution, and caution looks a lot like silence. This matters because 3i Atlas represents something potentially more significant than Oumuamua ever did. We have visible evidence now, not just inferred behavior. We have an object that appears to violate basic comet physics, and we have multiple opportunities to observe it being mysteriously unproductive in terms of the anomalies they reveal. Something is wrong with this picture, and figuring out whether that wrongness lies in the object itself or in our inability to study it properly might be one of the most important questions we can ask. Part 5. Why the Jet Matters. More than Oumuamua ever did. Let's talk about Oumuamua for a moment, because any discussion of interstellar anomalies has to reckon with what happened in 2017. Oumuamua was the first confirmed interstellar object to pass through our solar system, and it immediately didn't make sense. Its shape was wrong, either extremely elongated like a cigar or extremely flat like a pancake, depending on which brightness variations you believed. It accelerated on its way out of the solar system without any detectable outgassing to explain that acceleration. It tumbled in a way that suggested it wasn't a simple solid body. Loeb proposed the light sail hypothesis. Oumuamua might be an artificial object, a thin reflective surface designed to be pushed by stellar radiation. The astronomical community largely rejected this idea, not because it was impossible, but because it violated the principle that extraordinary claims require extraordinary evidence. We had no images of Oumuamua showing artificial structures. Everything we knew about it came from inferences based on how sunlight reflected off its surface and how its trajectory changed over time. Inferences can be wrong, models can fail. Jumping to aliens based on incomplete data is how you destroy your credibility as a scientist. 3i Atlas is different in a crucial way. We have an image. Not a detailed photograph showing rivets and antennas, but an image showing behavior that doesn't fit natural explanations. The jet pointing toward the sun is there in the data, captured across multiple exposures, consistent and persistent. You can't wave this away as easily as you could dismiss inferences about Oumuamua's shape or acceleration. The difference between acceleration and a visible jet is profound. Acceleration can be explained by many processes. Maybe we missed the outgassing because it was faint or pointed in a direction we didn't observe. Maybe the object's rotation created asymmetric thrust we didn't properly model. Explanations exist, even if they're not entirely satisfying. A jet pointing the wrong direction is harder to explain away. Jets are directional ejections of material. Physics tells us comets eject material away from the sun. If the material is going toward the sun, either our physics is wrong or something else is going on. Loeb frames the October 16th image as the visual proof we've been waiting for, the smoking gun that moves this discussion from speculation to something that demands serious investigation. Not proof of alien technology necessarily, but proof that our models of comet behavior are inadequate to explain what we're observing. That inadequacy means we need better explanations, and we need to be willing to follow those explanations wherever they lead. Mainstream science resists alien explanations for good reasons. History is littered with phenomena that seemed inexplicable until someone figured out the natural mechanism. Pulsars were briefly called LGM for little green men when they were first discovered. Regular radio pulses from space that seemed too precise to be natural. Then we realized they were rotating neutron stars and the mystery evaporated. Science works by trying every conventional explanation before entertaining unconventional ones. But there's a balance here. Being too skeptical of anomalies is just as dangerous as being too credulous. If you automatically dismiss everything that doesn't fit your models, you miss genuine discoveries. The history of science is also full of moments where establishment thinking rejected ideas that turned out to be correct because those ideas challenged comfortable assumptions. Continental drift was ridiculed until plate tectonics made it undeniable. Meteorites were considered superstitious nonsense until people actually studied them. Here's a speculative leap that might not be crazy. If Oumuamua was a reconnaissance mission, a quick flyby to scan our solar system, then 3i Atlas might be the follow-up visit. One object passes through, collects data, and moves on. Another arrives later with different objectives or capabilities. This isn't how natural objects behave. Comets don't coordinate. But if you're trying to understand what intelligent exploration might look like, sending multiple probes to the same system makes sense. The cultural context matters too. In 2017, when Oumuamua appeared, the idea of UFOs or UAPs was still largely taboo in mainstream discourse. The military UAP videos hadn't been officially released. Congressional hearings about unidentified aerial phenomena hadn't happened. Suggesting that an interstellar object might be artificial was career suicide. Now, in 2025, the conversation has shifted. UAP hearings occur regularly. Military personnel testify about encounters with objects displaying impossible flight characteristics. The stigma hasn't disappeared, but it's weakened. This cultural shift creates space for asking questions that would have been dismissed out of hand a few years ago. What if Oumuamua wasn't the first interstellar visitor? What if we've been missing these objects because we didn't know to look for them or didn't want to see what the data implied? What if 3i Atlas is one of many, and we're only noticing because its behaviour is too obvious to ignore? The stakes here extend beyond one comet or one image. If we're genuinely observing something artificial, something engineered, then everything changes. Our place in the universe, our understanding of what intelligence can accomplish, our assumptions about whether we're alone. These aren't abstract philosophical questions. They're practical issues that affect how we allocate resources, how we prioritize scientific research, how we think about humanity's future. But even if 3i Atlas turns out to have some exotic natural explanation we haven't thought of yet, the jet still matters. It matters because it shows our models are incomplete. It matters because it demonstrates that interstellar space can produce objects that challenge our expectations. It matters because the next anomaly might be even more dramatic, and we need to be ready to investigate it seriously rather than dismissing it out of hand. The October 16th image is a line in the sand. Before that date, you could argue that all the anomalies were subtle, ambiguous, subject to interpretation. After that date, we have a visible structure doing something comets don't do. That changes the conversation. That demands explanation. And the silence from institutional science, from Mars observations, from the Psyche mission, makes you wonder what else we're not being told. If this jet is real, and it appears to be, then maybe we need to consider that physics as we know it doesn't add up, at least not when applied to objects that might not be natural at all. Part 6. Physics that shouldn't work. Comets are simple, or at least they're supposed to be. You have a nucleus made of ice and rock, typically a few kilometers across, left over from the formation of a planetary system. This nucleus spends most of its time in the cold outer reaches of its home system, frozen solid, inactive. When it falls toward the sun, solar radiation heats the surface. Ice sublimates, turning directly from solid to gas without passing through a liquid phase. This gas carries dust particles with it, creating the characteristic coma and tail that make comets visible and beautiful. The physics is straightforward. Solar radiation pushes outward from the sun in all directions. When sunlight hits dust particles in the coma, it transfers momentum, pushing those particles away from the sun. The solar wind, that stream of charged particles flowing outward from the sun's corona, does the same thing to ionized gas molecules. The result is tails that always point away from the sun, like streamers blown by a cosmic wind. This is such a reliable phenomenon that ancient astronomers noticed it. Comet tails always point away from the sun regardless of whether the comet is approaching or receding. Anti-tails occasionally appear to violate this rule, but they're optical illusions. Sometimes a comet leaves a trail of dust particles along its orbital path, and when Earth passes through the plane of that orbit, the perspective makes it look like a tail pointing toward the sun. But this is geometry, not physics. The dust isn't actually moving sunward. It's sitting in place while we observe it from an angle that creates the illusion. You can verify anti-tails by tracking them over time. They disappear or change dramatically as viewing angles shift. The structure in the 3-eye atlas images doesn't behave like an anti-tail. Loeb's analysis describes a plume extending approximately 6,000 kilometers from the nucleus toward the Sun, visible across multiple observation sessions spanning weeks. This persistence rules out most geometrical explanations. 6,000 kilometers is not a trivial distance. It's roughly half the diameter of Earth. We're looking at a substantial feature, not a minor quirk in the data. If this plume is ejecting material toward the Sun, then something is producing forward thrust, pushing against the comet's orbital motion. Imagine you're on a bicycle coasting downhill. Natural processes are like gravity pulling you faster. What we're seeing with 3-eye atlas would be like someone pedaling uphill while coasting down, creating thrust in the opposite direction of your motion. That requires energy and a mechanism to convert that energy into directed force. Natural outgassing produces thrust, but it's disorganized, expanding in all directions from the heated surface. Some comets do experience non-gravitational forces from asymmetric outgassing. If one side of the nucleus is more active than the other, it can create a tiny rocket effect. But this effect is small and typically pushes the comet in random directions, not specifically toward the Sun. Getting sustained sunward thrust from natural processes requires a configuration that doesn't make physical sense. You'd need the most active regions of the nucleus to be on the Sun-facing side, continuously ejecting material directly toward the radiation source. Heat drives sublimation, so the Sun-facing side is where you'd expect activity. But that activity should create outward pressure, not inward thrust. Scientists considering conventional explanations have suggested imaging artifacts or unknown dust mechanics. Maybe the processing algorithm used to stack those 159 exposures created a false feature. Maybe there's some exotic dust behavior we don't understand that can appear to flow sunward. These are the kinds of explanations you grasp at when observations don't match theory. They're not satisfying because they require inventing new phenomena without independent evidence. Thousands of comets have been observed throughout history. Ancient records describe comets. Modern telescopes track dozens every year. We have detailed observations of cometary behavior spanning decades. None of them show sustained sunward jets. If such jets were a natural but rare phenomenon, we should have seen at least a few examples by now. The absence of precedent doesn't prove 3-eye atlas is artificial, but it strongly suggests that whatever's happening here isn't typical comet physics. Could this be deliberate propulsion? If you wanted to adjust a comet's trajectory, ejecting mass in a specific direction would do it. This is how rocket engines work. Throw mass out the back, and Newton's third law pushes you forward. A sunward jet would slow the object's orbital velocity, changing its path through the solar system. Why you'd want to do that is a separate question, but the mechanism is straightforward. What type of propulsion could create this effect? Chemical rockets would leave distinctive signatures in the spectrum, combustion products that should be detectable, ion, drives, which accelerate charged particles using electric fields, would produce different spectroscopic signatures. Solar sails wouldn't create jets at all, just passive reflection of sunlight. Some exotic propulsion system we don't understand. Now we're entering pure speculation, inventing technology to match observations. There's another possibility that sits uncomfortably in the space between natural and artificial. Maybe 3-eye atlas isn't a comet in the traditional sense. Maybe it's something we don't have a category for, an object formed through processes or in environments we've never encountered. The universe is capable of producing strange things. Neutron stars rotate hundreds of times per second and have magnetic fields trillions of times stronger than Earth's. Black holes warp space-time so severely that our equations break down. Why couldn't stellar systems produce objects that blur our categories? The problem with invoking unknown natural phenomena is that it's not much different from invoking aliens. Both explanations ask you to believe in something we have no other evidence for. The only difference is psychological. Unknown natural phenomena feel safer than artificial objects because they don't threaten our assumptions about being alone in the universe. But scientifically, both require evidence beyond the single anomalous observation. What we need are more observations, different instruments, multiple perspectives. We need spectroscopic analysis of the jet itself to determine its composition. We need trajectory calculations to see if the thrust is sustained or intermittent. We need follow-up images to confirm the structure persists and isn't some artifact of the original observation. Unfortunately, 3i Atlas is moving away from us now, getting fainter, becoming harder to observe. The window for detailed study is closing. This is the frustrating part of astronomical anomalies. They don't wait for you to build better instruments or organize observation campaigns. They pass through and disappear, leaving behind questions and ambiguous data. Oumuamua is now beyond Pluto's orbit, unreachable with current technology. 3i Atlas will follow the same trajectory, receding into interstellar space, and we'll be left arguing about images and spectra while the object itself becomes history. The sunward jet matters because it represents physical behavior we can't easily explain. It's not a statistical anomaly or an ambiguous signal. It's a structure in an image, something concrete that demands explanation. And when you start asking how such a structure could form and persist, the comfortable answers stop working. Natural processes fail to account for it. Unknown phenomena become appeals to ignorance. And the uncomfortable possibility that this object might not be natural becomes harder to dismiss. What if the laws of comet physics don't apply here because 3i Atlas isn't a comet? What if we're looking at something engineered? And that engineering includes the capacity to emit material in controlled directions for propulsion or other purposes we can't fathom? Part 7. Wild Hypotheses. Manufactured nickel engines. Let's talk about the nickel, because nickel keeps appearing in this story and nobody seems to have a good explanation for why. Spectroscopic observations of 3i Atlas detected emission lines characteristic of nickel in the comet's coma, the cloud of gas and dust surrounding the nucleus. This is unusual. Comets typically show emission from water, carbon monoxide, carbon dioxide, cyanogen, various organic compounds. Nickel isn't on the standard list. Nickel exists in space. Asteroids contain it, especially metallic asteroids that might be fragments of differentiated protoplanets where heavy elements sank to the core. Iron-nickel alloys are common in meteorites, but comets aren't supposed to be rich in metals. They form in the cold outer regions of planetary systems where volatile ices dominate. Rock and metal exist in comets, but as minor components, dust mixed with the ice. The dominance of nickel in 3i Atlas's spectrum suggests either an unusual formation environment or an unusual composition. Maybe this object formed in a region where metallic dust was more abundant than typical. Maybe it accreted material from a disrupted metallic asteroid. Maybe it's not primarily an icy comet, but something more like a metallic asteroid with some ice on it. Each explanation is possible, but each requires special pleading. Here's where the speculation gets interesting. Nickel has properties that make it useful for engineering. It's resistant to corrosion and high temperatures. Nickel alloys are used in jet engines and rocket nozzles, where materials have to withstand extreme heat and stress. If you are building a spacecraft or probe designed to travel through interstellar space and occasionally pass close to stars, nickel alloys would be a reasonable choice for structural materials. Could the nickel emission we're seeing be industrial byproduct? Could it be exhaust from some propulsion system that uses nickel-bearing fuel or ejects nickel as a reaction mass? This is pure speculation without evidence, but it's the kind of speculation that starts to make sense when you have multiple anomalies pointing in the same direction. The sunward jet suggests propulsion. The nickel suggests metallic composition inconsistent with typical comets. Put them together, and you get a hypothesis that feels uncomfortably plausible. The von Neumann probe concept provides a framework for thinking about self-replicating machines. Von Neumann, the brilliant mathematician and physicist, proposed the idea of machines that could reproduce themselves using raw materials from their environment. Send such a machine to another star system, and it could mine asteroids, build copies of itself, and send those copies to even more star systems. Over millions of years, a single civilization could explore the entire galaxy without ever leaving home, using exponentially replicating probes as their ambassadors. If 3i Atlas was some kind of probe, nickel could be both structural material and fuel. You arrive at a star system, identify metallic asteroids, extract raw materials including nickel, use those materials to repair yourself or build components, then continue your journey. The nickel emission might be waste products from processing or exhaust from propulsion. This is science fiction, but science fiction based on plausible engineering concepts. The alternative natural explanation invokes metallic comets, objects that formed with unusually high metal content. There's no physical law preventing such objects from existing. Formation conditions vary widely across different stellar environments. Maybe 3i Atlas's home star system had a different composition than our Sun, richer in heavy elements, producing comets that incorporate more metal. Maybe we're seeing the first example of a phenomenon that's common elsewhere but rare here. The problem with this explanation is that we've never observed a metallic comet in our own solar system despite studying thousands of them. If such objects exist naturally, they should occur here too, even if rarely. Their absence suggests that whatever 3i Atlas is, it's not just an unusual but natural variant. It's something fundamentally different. Another angle on the nickel mystery involves heat management. If an object were actively using propulsion systems, it would generate heat. That heat needs to go somewhere. Nickel's thermal properties make it useful for heat sinks and radiative cooling systems. The emission we're detecting might not be exhaust at all, but waste heat being radiated away from active systems. When metal gets hot enough, it glows and emits light at specific wavelengths, corresponding to the metal's atomic structure. What we're calling a gas plume might actually be vaporized metal being expelled as part of a cooling process. This takes us deeper into speculation, but consider what happens when you push any hypothesis to its logical extreme. If 3i Atlas is actively harvesting materials, processing them, and using them for propulsion or maintenance, it would need sophisticated systems we can barely imagine. It would need to identify suitable asteroids or comets, rendezvous with them, extract specific elements, refine those elements into usable forms, and integrate them into existing structures. This is technology far beyond current human capabilities, but it's not physics-defying, it's engineering, just very advanced engineering. The flip side of this speculation is that we might be seeing patterns where none exist. Humans are excellent at pattern recognition, so good that we often see faces in clouds and meaning in randomness. The nickel might have a boring explanation we haven't thought of yet. The jet might turn out to be an imaging artifact after all. The collection of anomalies might be exactly that, a collection of unrelated oddities that happen to occur in the same object by pure chance. But here's what keeps this hypothesis alive. The alternatives are almost as strange. If this is natural, we need new physics, or at least new understanding of how objects form and behave in conditions we've never encountered. If it's artificial, we need to accept that we're not alone, and that whoever built this is far more advanced than we are. Either conclusion is profound. Either conclusion changes everything. The question isn't whether we should believe in alien probes based on nickel emissions and weird jets. The question is whether we're willing to investigate thoroughly enough to rule out possibilities we'd rather not confront. Science advances by eliminating hypotheses until only the truth remains, no matter how uncomfortable that truth might be. Right now, we have insufficient data to eliminate anything definitively. We have tantalizing hints, suggestive patterns, and a growing sense that something important is happening just beyond our ability to fully understand it. And if this object is actively mining and processing materials as it travels through our solar system, could it also be communicating? Part 8. The Hidden Recordings. Theory. Amateur radio astronomers operate in a strange space between professional science and hobbyist enthusiasm. They have equipment sophisticated enough to detect signals from space, but not the institutional backing or peer review that professional observatories require. Sometimes this means they catch things that slip through the cracks of official observations. Sometimes it means they chase noise and convince themselves it's meaningful. Sorting signal from static requires careful analysis, and without professional vetting, it's hard to know what's real. During the Mars flyby in early October 2025, several amateur operators reported unusual signal spikes in radio frequencies they were monitoring. These weren't organized observations with proper protocols. They were individuals pointing antennas at interesting parts of the sky and recording what they found. The signals they reported were brief, intermittent, and at frequencies not typically associated with natural cosmic sources. None of the reports were verified by professional arrays. None were reproducible in the sense that other observers could confirm them independently. But the timing is interesting. If 3i Atlas were actively transmitting, either as a beacon or as telemetry sending data back to whoever launched it, the Mars flyby would be a logical time for increased activity. Close approach to another planet might trigger automated systems designed to gather and relay information. Think about how our own space probes behave. They conduct intensive observations during flybys, then beam that data back to Earth, when they have a clear line of sight and sufficient power. Now let's fold in another piece of this puzzle. Avi Loeb noted in his analysis that 3I Atlas's trajectory, traced backward through interstellar space, comes from a region of sky that includes the coordinates of the famous WOW signal. On August 15, 1977, the Big Ear radio telescope in Ohio detected a strong narrowband radio signal lasting 72 seconds. The signal was so unexpected and so strong that astronomer Jerry Eman wrote "Wow" in the margin of the computer printout. Follow-up observations never detected it again. It remains one of the most intriguing potential SETI detections ever recorded. The connection is speculative at best. The WOW signal came from a region near the constellation Sagittarius. 3I Atlas's trajectory passes through that general area of sky when traced backward, but space is three-dimensional and vast. Saying two things are related because they share a rough direction is like saying two cars are connected because they both drove north at some point. But what if the connection is real? What if the WOW signal was exactly what it appeared to be, a transmission from something artificial, and 3I Atlas is related to whatever sent that signal? Radio transmission makes sense for interstellar communication. Light travels fast, and radio waves are just light at lower frequencies. They propagate through interstellar space without significant absorption. They can encode enormous amounts of information. If you're sending probes to other star systems and want them to report back, radio is a logical choice. The distances are vast, so signals would take years or decades to reach home, but for a civilization thinking in timescales of millennia, that's acceptable. The counter-argument is straightforward. Professional SETI arrays have been listening to 3I Atlas and have reported no detections. The Breakthrough Listen initiative, funded by tech billionaire Yuri Milner and employing some of the most sensitive radio telescopes on Earth, specifically targeted Oumuamua and found nothing. They've presumably observed 3I Atlas too, though no press releases have announced results. If there were obvious signals, professional astronomers would have detected them. But institutional silence could apply here as well. SETI exists in an awkward position scientifically. It's legitimate in principle, searching for evidence of extraterrestrial intelligence using accepted methods. But it's also marginalized because it hasn't produced confirmed positive results in decades of searching. A false alarm would be embarrassing. Announcing a potential detection before being absolutely certain would invite ridicule. The incentive structure encourages extreme caution. What if SETI detected something ambiguous, a signal that might be artificial or might be natural, but not clear enough to announce publicly? What if the transmission is encrypted, or encoded in ways we don't recognize as communication? Human radio and television broadcasts look like structured signals because we know how to decode them. An alien transmission might appear as noise to our instruments. If we don't understand the encoding scheme, we assume communication will be obvious, but that assumption might be wrong. There's also the question of whether anyone is listening for the right type of signal. Traditional SETI focuses on narrow-band transmissions, artificial-looking signals at specific frequencies. Modern digital communication uses spread spectrum techniques that distribute signal energy across wide frequency ranges, making transmissions harder to detect but more resistant to interference. If an advanced civilization uses communication technology beyond our current methods, we might not recognize their signals even if we're drowning in them. The amateur reports of signal spikes during the Mars flyby could be nothing. Radio frequency interference from Earth sources, random noise, equipment malfunction, wishful thinking. The lack of professional confirmation suggests they probably are nothing. But the human history of discovery includes many instances where amateurs noticed things professionals missed, either because they were looking at the wrong place or because they dismissed anomalies that didn't fit expectations. Let's consider what it would mean if 3I Atlas is transmitting. It would mean the object is active, powered, and communicating with something. That communication could be internal, probe subsystems talking to each other as they coordinate observations and adjust trajectory. It could be external, sending data back to whoever launched it millions of years ago. It could even be directed at us, an attempt to make contact, or simply announce its presence to anyone capable of listening. The idea that we might be receiving messages and not recognizing them is simultaneously exciting and frustrating. It's like finding a book written in a language you've never seen. You know it contains information, but accessing that information requires decoding work you don't know how to do. Maybe the nickel emissions are data. Maybe the sunward jet pulses in patterns that encode meaning. Maybe we're looking at the communication and calling it anomalous physics because we don't understand what we're seeing. Or maybe there's nothing to any of this. Maybe 3I Atlas is exactly what it appears to be at first glance, a comet with some unusual properties but no deeper significance. The problem is that unusual properties keep accumulating, and at some point you have to ask whether you're dealing with a series of coincidences or a genuine phenomenon that doesn't fit your models. The hidden recordings theory remains speculation, but it's speculation that grows more plausible as the anomalies stack up. And if governments or institutions are hiding data, either about this object or about the broader question of non-human intelligence, the silence itself becomes evidence that something important is being obscured. Part 9, Institutional Playbook: Silence, Delay, Discredit. Pattern. Recognition is a powerful tool, but it's also a trap. See enough examples of similar behavior and you start to perceive patterns even in randomness. But sometimes patterns are real, and ignoring them because you're worried about apophenia, about seeing meaning where none exists, can blind you to genuine phenomena. The way institutions have handled 3I Atlas follows a playbook that's been used before, and recognizing that playbook doesn't require conspiracy thinking, just attention to how organizations behave when faced with information they don't know how to process. The timeline goes like this. In July 2025, Hubble Space Telescope observations captured a faint feature extending from 3I Atlas. Scientists noted it in their logs but didn't publish immediately. Space science generates enormous amounts of data and analysis takes time. The feature was ambiguous, possibly an artifact, possibly real. Standard procedure is to investigate thoroughly before making public claims. By September, the Mars orbits were in position to observe the comet during its close approach. Images were taken, data was collected, and some results were released showing the comet as expected. No press releases highlighted anomalies, no papers discussed unusual jets or propulsion signatures. The narrative presented to the public was routine, a comet doing comet things, mildly interesting, but nothing extraordinary. In October, the 2-meter twin telescope captured images clearly showing the sunward jet. This observation came from outside institutional channels, independent astronomers with their own equipment operating without need for approval from funding agencies or review boards. They published their findings and Loeb amplified them. Suddenly the anomaly was public, and institutions had to respond. The response followed a predictable pattern. First came silence, days and weeks without official comment from major space agencies. When comments did come, they emphasized caution and alternative explanations. Processing artifacts were mentioned. The need for more data was stressed. The tone was, let's not get ahead of ourselves, which is reasonable in science, but also serves to downplay findings that might be uncomfortable. Then came delays in releasing data. Mars flyby observations should have produced detailed images and spectra that could confirm or refute the sunward jet. Those datasets exist, collected by instruments that observe the comet at close range, but comprehensive public releases have been slow. Technical papers will appear eventually after peer review and institutional vetting, and by that time the moment of excitement will have passed. The public will have moved on to other topics. Finally comes discrediting, not necessarily of the observations themselves, but of the implications people draw from them. Scientists who suggest non-natural explanations get labelled as fringe, attention-seeking, or insufficiently rigorous. Loeb has experienced this throughout his career whenever he proposes that anomalous objects might be artificial. The response isn't to address his arguments directly, but to dismiss them as speculative or unscientific. This is the playbook. Silence until you can't maintain it. Delay while you craft acceptable explanations. Discredit those who won't accept the official narrative. It's not unique to space anomalies. You see it in any field where challenging established consensus threatens institutional stability. Climate science saw it when fossil fuel interests wanted to downplay global warming. Medicine saw it when tobacco companies wanted to obscure cancer links. The mechanics are the same, just applied to different contexts. Oumuamua provides a clear historical parallel. When that object displayed unexplained acceleration, the initial response was silence and confusion. Papers eventually proposed outgassing as the explanation, but those papers required invoking special conditions that made the models work. Loeb's light sail hypothesis was rejected not because it was disproven, but because it was too radical. The scientific community closed ranks around conventional explanations, and Oumuamua receded into interstellar space with its mysteries unresolved. UAP hearings before Congress show the same pattern. Military personnel testify about encounters with objects displaying flight characteristics beyond known technology. Official responses emphasize the need for further study, while avoiding any acknowledgement that something genuinely anomalous might be happening. Data remains classified. Investigations proceed behind closed doors. The public receives carefully curated information designed to neither confirm nor deny anything significant. Even the James Webb Space Telescope has participated in this pattern. When Webb's first deep-field images revealed more distant galaxies than theoretical models predicted, initial excitement gave way to careful hedging. Papers explained how the observations could fit within existing frameworks with minor adjustments. The possibility that cosmological models might need fundamental revision was downplayed in favor of incremental modifications that preserve established theory. Why do institutions behave this way? Because anomalies are dangerous. They threaten funding by suggesting previous work missed important phenomena. They invite ridicule from skeptics who will use any speculation against you in political battles over budgets. They open doors to uncomfortable questions about what else might have been missed or ignored. Organizations optimize for stability and continued operation, not for revolutionary discoveries that overturn comfortable assumptions. There's also the fear of panic to consider. If NASA announced that an interstellar object showed signs of artificial construction, what would happen? Media frenzy certainly, with every outlet demanding answers nobody has. Public alarm possibly, as people worry about alien intentions. Political exploitation definitely, as various factions use the discovery to advance their agendas. The safer choice is to say nothing until you're absolutely certain, and absolute certainty never arrives because anomalous data is always ambiguous. Historical analogies abound. Galileo faced persecution not just for being wrong by church standards, but for challenging the institutional authority of the church to determine truth. His observations threatened a power structure, and that structure defended itself by silencing him. Cold War UFO cover-ups, whether you believe they involved aliens or just misidentified aircraft, followed similar patterns: official denials, classified documents, ridicule of witnesses. The goal was to maintain control of the narrative regardless of underlying truth. We've reached a point where the public no longer automatically trusts official narratives. Trust in institutions has eroded across multiple domains, not because of specific conspiracies necessarily, but because institutions have been caught lying, obfuscating, or simply being wrong too many times. When space agencies now say, "There's nothing unusual happening," a significant portion of the population hears, "There's something they're not telling us." This trust gap is dangerous in some ways. It fuels conspiracy theories that go far beyond evidence. It makes rational discussion harder when everything is seen through a lens of suspicion. But it also serves a function. It keeps pressure on institutions to be transparent and to justify their conclusions. It creates space for alternative voices like Loeb's to be heard even when they contradict official positions. The bigger question is what happens if the silence is hiding something real? If 3i Atlas genuinely shows evidence of artificial construction or exotic propulsion, and that evidence is being suppressed or downplayed, then we're collectively missing one of the most important discoveries in human history. The playbook that works for managing public expectations around incremental science becomes actively harmful when applied to paradigm-shifting observations. But by the time anyone realizes a paradigm is shifting, institutional momentum has already committed to the strategy of silence, delay, and discrediting. And once you're committed to that strategy, admitting you were wrong becomes nearly impossible without sacrificing careers and credibility. So the question becomes not whether anomalies exist, but whether we're capable as a civilization of confronting them honestly when institutional incentives point in the opposite direction. Part 10. Beyond 3i Atlas. The bigger chessboard. Space has never been purely about science. From the moment humans looked up and wondered about the stars, those questions mixed with concerns about power, security, and advantage over rivals. The space race between America and the Soviet Union wasn't driven by astronomical curiosity. It was a demonstration of technological capability, a proxy war fought with rockets and satellites instead of bombs and bullets. That dynamic never went away. It just evolved. Today's space environment is more militarized than most people realize. The United States Space Force, established in 2019, operates satellites for communication, navigation, surveillance, and missile warning. China has demonstrated anti-satellite weapons capable of destroying orbital infrastructure. Russia conducts tests of orbital platforms that could theoretically disable or capture other nations' satellites. Space is no longer the peaceful domain of scientific exploration that treaties signed in the 1960s tried to establish. It's contested territory where strategic advantage matters. If 3i Atlas is artificial, if it genuinely represents technology from another civilization, then it immediately becomes a strategic object, not just scientifically interesting, but potentially valuable or threatening depending on what it's doing and what it might contain. Advanced propulsion technology, material science beyond our current capabilities, computing architectures we haven't conceived, energy systems that could revolutionize power generation. Any of these would represent enormous strategic value to whoever could access and understand them. Governments might hide anomalies not to prevent public panic, but to prevent adversaries from gaining information. If American instruments detected something unusual about 3i Atlas, would they share that data openly with the world? Or would they classify it, study it secretly, and hope to extract strategic advantage before rivals do the same? This isn't paranoia. This is how nations behave when strategic interests are at stake. The Cold War saw countless examples of scientific discoveries being immediately classified because of potential military applications. Past UFO secrecy, whether you believe it involved alien craft or just advanced Soviet aircraft, followed exactly this logic. The US military didn't want potential adversaries knowing what American radar could detect or how pilot encounters were being analyzed. Secrecy served strategic purposes independent of whether the underlying phenomena were extraordinary or mundane. The same logic applies to interstellar objects showing anomalous behavior. Could multiple nations already know that something unusual is happening with 3i Atlas and be competing for advantage? China has a sophisticated space program capable of independent observations. Russia maintains astronomical capabilities despite economic constraints. The European Space Agency operates instruments that rival NASA's insensitivity. If any of these organizations detected unambiguous evidence of artificial construction, would they announce it publicly, or would they classify the information and begin quiet programs to learn more? The nightmare scenario from a strategic perspective is that someone else figures it out first. If China developed an understanding of 3i Atlas's propulsion system before the United States did, that would represent a technological leap potentially decisive in future conflicts. The incentive to keep things secret, to prevent rivals from even knowing there's something worth investigating, becomes overwhelming. The scientific community's desire for open sharing of data crashes into the military strategic imperative to deny adversaries any potential advantage. Space law exists, but barely. The Outer Space Treaty of 1967 prohibits nations from claiming celestial bodies as sovereign territory and bans weapons of mass destruction in orbit. But it's vague on everything else, and enforcement mechanisms are essentially non-existent. If a nation decided to capture an asteroid for mining, or to intercept an interstellar object for study, what would stop them beyond the practical difficulties? The legal framework for space activity was written when spaceflight was nascent, and it hasn't kept pace with technological developments or shifting geopolitical realities. If 3i Atlas is artificial, militarization narratives become unavoidable. Defense establishments in multiple countries would immediately begin asking questions. Could this object be hostile? Could it be gathering intelligence? Could it be a precursor to something more significant? The fact that it approached Mars, a planet where multiple nations operate spacecraft, would heighten these concerns. The fact that it displays apparent propulsion capability would trigger threat assessments. Even if the object is entirely benign, a relic from some long-dead civilization drifting through space on autopilot, it would be treated as a potential threat until proven otherwise. This explains why anomalies might be downplayed publicly. Acknowledging them openly invites questions about what's being done to investigate or respond. Those questions lead to classified programs that nations don't want to discuss. The simplest approach is to deny that anything unusual is happening until such time as denial is no longer tenable. By then, hopefully, you've gained enough understanding to control the narrative and mitigate strategic risks. 3i Atlas becomes a pawn on a chessboard, most people don't even know exists, moved by forces operating beyond public view. Science wants to study it openly, sharing data and collaborating across borders. Strategy wants to exploit it secretly, denying information to rivals and maximizing national advantage. These two imperatives cannot be reconciled. One of them must yield, and history suggests science usually loses when strategic interests are invoked. The urgency here extends beyond academic questions, about whether we're alone in the universe. If advanced technology is passing through our solar system, accessible for study or even acquisition, then whoever gets there first gains advantages that could shape geopolitics for generations. This isn't just about understanding alien engineering. It's about ensuring your nation isn't left behind while others leap forward. It's about preventing adversaries from gaining capabilities that could threaten your security. These are the calculations happening in classified briefings, far removed from public discourse about comets and anomalies. And here's the truly unsettling thought. If this is how nations behave when faced with a single anomalous object, what happens when multiple breakthroughs occur simultaneously across different frontiers? What if we're living through a moment when several long-promised advances all converge at once, each with its own strategic implications, each creating pressure for secrecy and competitive advantage? Because 3i Atlas isn't the only story unfolding in 2025, it's just the one that's hardest to ignore. Part 11. Dark Matter Detection Controversy. Dark matter is embarrassing for physics in a way that's hard to explain to non-scientists. We've known about it for almost a century. We know it must exist because galaxies rotate in ways that don't match the visible mass they contain. We know it outweighs ordinary matter by a factor of 5 to 1. We've built elaborate theories about what it might be, exotic particles that interact with normal matter only through gravity. And despite decades of searching with increasingly sophisticated experiments, we haven't definitively detected it. October 2025 brought new results from underground laboratories in Italy and Japan. These facilities buried deep beneath mountains to shield them from cosmic rays and other background radiation. House detectors designed to catch the faint interactions that would signal dark matter particles passing through Earth. The newest data shows slight excesses over expected background, more events than random noise should produce, at energy levels consistent with some dark matter models. The physics community is cautiously excited and deeply skeptical in roughly equal measure. We've been here before. Past experiments reported possible dark matter signals that later turned out to be instrumental effects or misunderstood backgrounds. The Dharma experiment in Italy has claimed a dark matter detection for years, an annual modulation in their signal that matches predictions for how dark matter interactions should vary as Earth orbits the Sun. Other experiments haven't confirmed it. The field is littered with false dawns. What makes the 2025 results different is their statistical strength and the fact that multiple independent detectors are seeing similar excesses. The Italian team uses xenon as their detection medium, looking for tiny flashes of light when dark matter particles scatter off xenon nuclei. The Japanese team uses a completely different approach with cryogenic crystals that detect phonons, quantum vibrations in the crystal lattice. The technologies are dissimilar enough that systematic errors affecting one shouldn't affect the other, yet both show hints of something at similar energy ranges. Dark matter represents one of the greatest mysteries in physics because it reveals how little we understand about the universe's composition. Everything we can see, stars and planets and nebulae and galaxies, all the ordinary matter made of protons and neutrons and electrons, accounts for less than 20% of the total mass. The rest is invisible, interacting with light so weakly that it passes through ordinary matter almost without trace. We infer its existence from gravitational effects, the way galaxies bend light from more distant objects, and the way galaxy clusters hold together despite insufficient visible mass. If the new detections are real, they would help explain not just dark matter's existence but its properties. The mass of the particle, its interaction strength, how it clumps and distributes through space. This information could revolutionize cosmology and particle physics. It could also, speculatively, help explain interstellar objects' anomalies. If dark matter interactions are stronger than expected, could they affect trajectory calculations? Could objects passing through regions of dense dark matter experience forces we haven't accounted for? This is wild speculation without supporting evidence, But anomalies in one domain sometimes connect to anomalies in others. Skepticism about the new results focuses on the same issues that plagued previous claims. Background events are fiendishly difficult to characterize completely. Radioactive contaminants in detector materials, cosmic rays that slip through the shielding, even neutrinos from the sun can create signals that mimic dark matter. You need years of data and painstaking analysis to distinguish true signal from background noise. The current results, while suggestive, aren't yet at the level of confidence physicists require for claiming discovery. Why detection technology overlaps with SETI is interesting. Both fields search for faint signals against enormous backgrounds. Both require extreme sensitivity to subtle effects. Both need sophisticated statistical methods to separate potential discoveries from noise. The techniques developed for dark matter detection, shielding, and background rejection, and low-threshold sensors could be adapted for detecting other weak signals, including potential technosignatures from extraterrestrial civilizations. There's also a funding angle. Dark matter research has absorbed billions of dollars over decades, justified by the importance of understanding the universe's composition. If those experiments continue to find nothing definitively, support eventually erodes. Positive results, even tentative ones, renew enthusiasm and unlock additional resources. The pressure to report discoveries, even ambiguous ones, is real. Scientists are human and subject to the same biases and incentives as anyone else. The speculative link between dark matter and 3I Atlas is tenuous at best. Dark matter interacts so weakly with ordinary matter that it's hard to imagine how it could produce visible effects like sunward jets. But physics is full of surprises, phenomena that seem impossible until someone figures out the mechanism that makes them work. Maybe there are dark matter interactions we haven't discovered yet, energy transfer processes that could affect object trajectories or even power exotic propulsion systems. Public excitement about potential dark matter detection reflects a hunger for fundamental discoveries. People want to live in an era when big questions get answered, when the universe reveals its secrets. The 21st century has seen incredible advances in applied technology, smartphones and AI, and genetic medicine, but fewer paradigm-shifting discoveries in fundamental physics. The Higgs boson was found in 2012, confirming predictions from the 1960s. Gravitational waves were detected in 2015, confirming predictions from 1915. We're validating old theories more than discovering new ones. Institutional caution around announcing dark matter detection mirrors the caution around 3I Atlas anomalies. Nobody wants to be the scientist who cried discovery, only to have it evaporate under scrutiny. Careers hinge on being right about big claims. The incentive structure punishes false positives more severely than it rewards true positives, so scientists hedge and qualify, and wait for overwhelming evidence before committing. This is usually good practice, but it can delay recognition of genuine discoveries. The broader context here is that multiple frontiers in physics and astronomy are active simultaneously in 2025. Dark matter hints, interstellar anomalies, advances in other fields all pushing boundaries at once. This clustering might be coincidence, or it might reflect underlying connections we haven't recognized yet. Sometimes scientific progress happens in bursts, periods when several pieces click into place at once, because they're all aspects of a larger picture finally coming into focus. And speaking of advances that have been promised for decades, fusion energy is suddenly looking less like a perpetual pipe dream and more like an imminent reality. Part 12. Breakthrough in fusion power. Fusion has been 30 years away for about 70 years now, a running joke in physics about promises that never materialize. The concept is simple. Smash light atomic nuclei together hard enough, and they fuse into heavier nuclei, releasing enormous energy in the process. This is how stars work. Gravitational pressure creating temperatures and densities sufficient for fusion. On Earth, without star mass gravity, you need different approaches, magnetic confinement or inertial confinement, each with its own technical nightmares. The breakthrough announced in 2025 comes from a private startup using AI-controlled plasma shaping, a technique that adjusts magnetic field configurations in real time to maintain plasma stability. Fusion requires heating hydrogen isotopes to temperatures exceeding 100 million degrees Celsius. At those temperatures, matter becomes plasma, a soup of ionized particles that doesn't want to stay confined. Historically, plasma instabilities have been the bane of fusion research. You heat the fuel, containment fails, plasma touches the reactor walls and cools, fusion stops. The new approach uses machine learning algorithms trained on thousands of simulated plasma configurations. The AI predicts instabilities before they develop and adjusts magnetic fields to suppress them. It's doing calculations and making corrections faster than human operators could, maintaining confinement for longer periods and achieving higher fusion rates. The net energy gain, energy out exceeding energy in, reached record levels in recent experiments. Not yet at commercial viability, but closer than ever before. Why this matters extends beyond clean energy, though that alone would be revolutionary. Fusion represents essentially unlimited power. Deuterium, one of the fuel isotopes, can be extracted from seawater. The fuel supply would last billions of years. No greenhouse gas emissions, no long-lived radioactive waste like fission reactors produce, just helium as a byproduct. It's the energy source science fiction promised us, finally becoming plausible in reality. For space exploration, fusion opens possibilities currently science-fictional. Fusion rockets could achieve exhaust velocities far higher than chemical rockets, making travel to outer planets practical and interstellar missions conceivable. You'd still need decades to reach even the nearest stars, but decades beats millennia. Suddenly those discussions about sending probes to Alpha Centauri or Proxima Centauri shift from theoretical exercises to engineering challenges. This connects directly to 3I Atlas's mysterious jet. If we're on the verge of fusion technology, maybe we'll finally understand propulsion systems that could produce sunward thrust or sustained acceleration without visible fuel consumption. Advanced civilizations millions of years ahead of us would presumably have solved fusion long ago and moved on to even more sophisticated energy sources. The jet we're seeing might be fusion exhaust, or something beyond fusion we don't have concepts for yet. Historical struggles with fusion are legendary. ITER, the International Thermonuclear Experimental Reactor, is a massive collaborative project involving 35 nations that's been under construction in France for decades and still hasn't achieved first plasma. Budget overruns and timeline delays plague the project. The National Ignition Facility in California did achieve fusion ignition in 2022, where fusion reactions produced more energy than the lasers delivered to the fuel, but the lasers themselves required enormous energy input, so net system energy remained negative. Private fusion startups have proliferated in recent years, each pursuing different technical approaches and claiming they'll reach commercial viability within a decade. Most will probably fail. Some might succeed. The influx of private capital and entrepreneurial energy into fusion research represents a shift from the decades when only governments funded these efforts. Venture capitalists smell opportunity, and while their timelines are often optimistic to the point of absurdity, their money accelerates development. Skepticism about fusion announcements is warranted. Every few years, someone claims a breakthrough that will lead to power plants within a decade. Those decades pass and plants don't materialize. The physics of fusion is understood. The engineering remains brutally difficult. Reactor materials that can withstand neutron bombardment, tritium breeding to supply fuel, heat extraction to convert fusion energy to electricity. Each problem has solutions in theory but implementation challenges in practice. But the 2025 results feel different. The gains are measurable and verified by independent observers. The AI approach to plasma control represents a genuinely new technique rather than incremental improvements to existing methods. Major energy companies and governments are investing seriously rather than just funding research grants. The convergence of technologies, high-temperature superconductors for magnets, advanced materials for reactor walls, AI for control systems, creates opportunities that didn't exist a decade ago. There's a conspiracy angle some people push that fusion breakthroughs are being timed deliberately to distract from space anomalies. Big announcement about clean energy drowns out coverage of mysterious comets. This is probably nonsense. Fusion research proceeds on its own timeline driven by technical progress, not public relations strategy. But the coincidence of multiple frontiers advancing simultaneously in 2025 is striking. It might be meaningful, or it might just be how progress happens, in clusters rather than smooth continuous lines. The transition from fusion to artificial intelligence is natural because AI drives the fusion progress. Machine learning isn't just optimizing plasma configurations, It's revolutionizing how we search for patterns in massive data sets, including astronomical observations that might reveal planets or anomalies humans would miss. Part 13. AI discovered exoplanet candidates. The Kepler Space Telescope operated from 2009 to 2018, staring at a single patch of sky containing over 100,000 stars, looking for the tiny dips in brightness that occur when planets pass in front of their stars. Those 9 years of observations produced a dataset so large that human astronomers are still analysing it. Every transit event had to be examined to determine whether it was a real planet or a false positive, caused by binary stars or instrumental noise. Artificial intelligence offers a different approach. Train neural networks on confirmed planets so they learn what real transits look like, then turn them loose on the full dataset, including portions humans haven't thoroughly examined. The AI doesn't get bored or tired. It can process millions of light curves in hours, flagging candidates that meet its learned criteria for genuine planets. Fall 2025 saw announcements of dozens of new Earth-size candidates overlooked in previous human-led analyses. Why AI outperforms human eyes comes down to pattern recognition at scale. Humans are excellent at recognizing patterns in small datasets. We can look at a light curve and intuitively sense whether a dip looks planet-like. But when you have millions of light curves, human attention becomes the bottleneck. We miss subtle patterns, especially in noisy data where signals are barely distinguishable from background variation. Neural networks excel exactly where humans fail, finding weak signals in massive datasets by learning what combinations of features indicate real phenomena. The implications extend beyond just finding more planets. If AI can spot subtle planetary transits humans miss, could it identify anomalies in 3i Atlas data that conventional analysis overlooks? Feed all the observations, spectroscopic data, images, trajectory measurements into a neural network trained to identify patterns that don't match known natural objects. Maybe the AI would recognize signatures of engineering that look like noise to human astronomers trained to expect comets. There's institutional reluctance to accept AI findings, similar to reluctance about accepting Loeb's interpretations of anomalous data. Traditional science values human judgment and understanding. You're supposed to know why something is true, not just that a black box algorithm says it's true. Neural networks are famously opaque. They make predictions based on learned patterns, but explaining exactly why they classified something one way versus another is difficult. This opacity troubles scientists who value explainability. Consider what happens when an AI flags a planet candidate that human astronomers previously rejected. The human looked at the data and decided it was probably a false positive, maybe stellar variability or instrumental noise that mimicked a transit. The AI, trained on thousands of confirmed planets, says no, this pattern matches real planets more closely than it matches false positives. Who's right? The answer requires follow-up observations, often years of additional data collection to confirm or refute the detection. Until then, you're stuck with competing assessments based on different methodologies. The speculative angle here gets interesting. What if AI could be the first to recognize alien engineering because it's not constrained by human assumptions about what's natural versus artificial? We've spent centuries studying comets and asteroids, building intuitions about how these objects behave. Those intuitions are powerful but also limiting. When something violates our expectations, our first instinct is to doubt the observation rather than doubt the expectations. An AI trained on data rather than theory might be more open to patterns that don't fit conventional categories. This has happened before in different contexts. Machine learning algorithms analyzing medical images sometimes outperform human radiologists, not because they see things humans can't see, but because they don't carry the biases human experts develop through training. A subtle pattern in an X-ray that experienced doctors dismiss as artifact might actually be an early sign of disease that the AI recognizes because it learned from thousands of confirmed cases without developing the heuristics humans use to filter information. Apply this to astronomy, and you get a framework for thinking about anomaly detection differently. Instead of asking whether 3i Atlas fits our models of comets, you ask an AI to classify it based on everything we know about solar system objects. If the AI consistently categorizes it as an outlier, as something that doesn't cluster with any known object type, that tells you something important even if the AI can't explain in human terms why it reached that conclusion. The Breakthrough Listen initiative, that SETI project backed by private funding, has started using machine learning to search for technosignatures in radio telescope data. Traditional SETI looks for narrowband signals at specific frequencies, patterns that would be obviously artificial, but maybe alien transmissions don't look like that. Maybe they use spread spectrum techniques or encoding schemes we haven't imagined. An AI trained on both natural cosmic signals and human communication could potentially recognize structured patterns that look like noise to traditional analysis. Historical echoes resonate here. When Copernicus proposed that Earth orbits the Sun rather than the reverse, he violated centuries of astronomical tradition. The evidence was always there in the retrograde motion of planets and the varying brightness of Mars, but geocentric models had become so elaborate, so good at explaining observations within their framework, that breaking free required a complete paradigm shift. Sometimes the barrier to discovery isn't lack of data, but inability to interpret data outside existing frameworks. We might be in a similar position now with interstellar objects and anomalous phenomena. The data exists, images and spectra and trajectory measurements. What we lack is the interpretive framework that makes sense of patterns that don't fit conventional categories. AI offers a potential path forward, precisely because it doesn't carry our conceptual baggage. It learns from data what patterns exist without requiring those patterns to conform to theoretical expectations developed from limited historical experience. The practical challenge is trusting AI conclusions enough to invest resources in following up its predictions. If a neural network says 3i Atlas shows patterns consistent with artificial objects based on spectroscopic signatures we've dismissed as noise, do you devote telescope time to gathering more data? Do you publish results based on AI analysis even though you can't fully explain the AI's reasoning? These are judgment calls that make scientists uncomfortable because they require accepting conclusions without complete understanding of how those conclusions were reached. Yet this is increasingly how science operates in the age of big data. Particle physics uses machine learning to identify collision events in detectors that produce millions of events per second. Genomics uses AI to predict protein structures from amino acid sequences. Climate science uses neural networks to model complex atmospheric interactions. The technique works, producing results that advance knowledge, even when the internal workings of the models remain partially opaque. The exoplanet discoveries represent a proof of concept. AI can find things humans miss in astronomical data. The question is whether we're willing to extend this approach to searching for phenomena we're not sure exist. Looking for planets is safe because we know planets exist. Looking for alien technology is risky because you're hunting for something that might not be there, and false positives damage credibility. But here's the thing about transformative discoveries. They often come from exactly this kind of risk-taking. You have to be willing to look for things you're not certain exist, using methods you don't fully understand, accepting that most searches will fail, but knowing that the rare success changes everything. The exoplanets AI discovered in Kepler data were there all along. They were just invisible to human analysis constrained by assumptions about what planetary signals should look like. What else is hiding in plain sight in our astronomical datasets? What patterns exist in observations of 3i Atlas or other anomalous objects that we've filtered out as noise because they don't match our expectations? Machine learning might reveal those patterns if we're brave enough to look, and honest enough to take the results seriously even when they challenge comfortable assumptions about what's possible. The timing of these AI discoveries in fall 2025, coinciding with the 3i Atlas revelations and other frontier advances, might be pure coincidence. Or it might reflect something deeper, a convergence of capabilities and questions that creates unique opportunities for breakthrough understanding. We've built tools powerful enough to see patterns beyond human cognitive limits. We've encountered phenomena that don't fit existing frameworks. The combination creates potential for discoveries that weren't possible even a decade ago, and if AI is revolutionizing how we find planets, by recognizing subtle patterns in light curves, imagine what it could do, analyzing the even more subtle patterns that might exist in signals we've always assumed were just background noise. Which brings us to another frontier where AI and advanced technology are creating capabilities we've never had before, the realm of quantum communication, where information might be transmitted in ways that bypass classical physics entirely. Part 14. Quantum Communication, Satellite Launch. Quantum mechanics is uncomfortable. It describes reality in ways that violate intuition, Particles existing in superposition of multiple states until measured, entangled particles affecting each other instantly across arbitrary distances, the act of observation changing what's being observed. Einstein called entanglement spooky action at a distance, because he found it philosophically troubling even though the math predicted it and experiments confirmed it. That discomfort hasn't stopped physicists from exploiting quantum phenomena for practical applications. 2025 saw China and the European Space Agency testing quantum-encrypted communication satellites. These aren't experimental demonstrations anymore, but operational systems designed to provide secure communication channels immune to classical eavesdropping. The principle relies on quantum key distribution, using entangled photons to establish encryption keys between distant parties. Any attempt to intercept the key changes the quantum states in detectable ways, alerting users that the channel has been compromised. The promise of quantum communication extends beyond security. Theoretical frameworks suggest quantum networks could enable faster information transfer than classical systems, not by transmitting data faster than light, which physics forbids, but by using quantum correlations to reduce the information that needs to be transmitted. It's subtle and requires understanding quantum information theory. But the practical upshot is communication systems with capabilities no classical network can match. Could alien civilizations use quantum entanglement for communication? This is speculation layered on speculation, but consider the engineering problem of interstellar communication. Light speed lag becomes prohibitive across stellar distances. A message sent from Earth to the nearest star system takes over 4 years to arrive. A reply takes another 4 years. Conversation is impossible. Any communication must be one way. Transmission of information without expectation of timely response, unless you have quantum entanglement. If you could prepare entangled particles, take one set on your journey and leave the other set at home, measurements on one set would correlate with measurements on the other set regardless of distance. This doesn't actually allow faster-than-light communication in the conventional sense. You can't transmit specific messages through entanglement alone. But maybe advanced physics we don't understand yet could exploit quantum correlations for communication in ways that bypass light speed limitations. The 3I Atlas anomalies viewed through this lens take on different character. What if the object isn't transmitting radio signals but using quantum communication methods we don't have the technology to detect? What if the hidden recordings aren't hidden at all but encoded in quantum states that classical instruments can't measure? This sounds like fantasy, but a century ago quantum mechanics itself sounded like fantasy. Our current understanding of physics isn't complete, and the gaps in that understanding might contain communication mechanisms we haven't imagined. Why institutions fear falling behind in quantum technology is straightforward. Quantum computing threatens current encryption standards. Quantum networks could provide communication channels that rivals can't intercept. Quantum sensing enables detection of phenomena invisible to classical instruments. These capabilities represent strategic advantages potentially decisive in conflicts or competition. The nation that achieves quantum supremacy first gains leverage that others cannot easily counter. Past secrecy around cryptography breakthroughs provides context. During World War II, British mathematicians cracked German Enigma codes, giving the Allies access to enemy communications. The British kept this secret not just from the Germans but from their own public, even after the war ended, because the techniques developed were too valuable to reveal. Similar secrecy surrounded American efforts to develop public key cryptography in the 1970s. Technologies that provide communication security or code-breaking capability are immediately classified because they're too strategically valuable to share. Quantum communication falls into this category. If China has operational quantum satellites providing secure communication, that's a capability the United States wants to match or counter. If either nation discovers a way to exploit quantum phenomena for faster than light, or at least faster than classical information transfer, that discovery gets classified immediately. The incentive structure ensures that breakthrough advances in this domain won't be announced publicly until they're either impossible to hide or already obsolete. How this ties to the hidden recordings theory around 3I Atlas is admittedly tenuous, but consider the possibility that we're looking for communication in all the wrong ways. Radio SETI assumes aliens use electromagnetic radiation at frequencies we can detect with our instruments. What if advanced civilizations abandoned radio millions of years ago in favor of quantum channels that are essentially invisible to classical detectors? We'd be like someone searching for internet traffic by listening for telegraph clicks, using obsolete technology to search for signals transmitted through methods we don't understand. The analogy works better than it might seem. Early human communication used smoke signals and drums, then progressed to telegraphs and radio, then fiber optics and satellite links, now quantum networks. Each generation of technology is essentially invisible to instruments designed for the previous generation. A radio receiver won't detect fiber optic transmissions. A classical antenna won't pick up quantum encrypted satellite communications. If we're using early 21st century instruments to search for communications from civilizations millions of years more advanced, the chances of success approach zero unless they're deliberately transmitting in ways we can detect. Maybe that's what the wow signal was, a deliberate transmission in a format we could recognize, a hello sent using technology we'd be capable of detecting. Maybe 3i Atlas is a follow-up, not transmitting because it doesn't need to, using quantum communication to report its observations back to whoever sent it through channels we don't have the physics to access. This is pure speculation without supporting evidence, but it illustrates how our assumptions about communication constrain what we look for and what we're capable of finding. The public remains largely unaware of how fast quantum technology is advancing. Popular coverage focuses on quantum computing and the threat it poses to current encryption. Less attention goes to quantum networks and sensing applications that are equally revolutionary in their implications. China's quantum satellite, Michus, launched in 2016 and demonstrated quantum key distribution between ground stations separated by thousands of kilometers. The 2025 missions represent operational deployments of technology that was experimental less than a decade ago. European contributions focus on creating quantum networks between ground stations and satellites, building infrastructure for a future quantum internet. The potential applications extend beyond secure government communication to financial transactions requiring absolute security. Distributed quantum computing, where multiple quantum computers work together on problems too large for individual systems, quantum sensing networks that could detect gravitational waves or other subtle phenomena through quantum entanglement of distant sensors. This last application is particularly intriguing in the context of anomaly detection. If you could create quantum entangled sensors distributed across the solar system, they might detect correlations or patterns invisible to classical instruments. Imagine quantum sensors on Earth, Mars, and various satellites all entangled and sharing quantum information. They might perceive 3i Atlas differently than classical telescopes do, seeing quantum signatures associated with propulsion or communication systems that operate on principles we're only beginning to understand. The challenge is that quantum technology is fundamentally different from anything that came before. You can't just upgrade classical systems to detect quantum phenomena. You need entirely new instruments built from scratch, using principles that seem counterintuitive. This means we might be blind to entire categories of phenomena not because they're rare or subtle, but because we lack the right tools to perceive them. Historical parallels exist throughout science. Before microscopes, we didn't know about bacteria and cells. Before telescopes, we couldn't resolve planets as disks or see Jupiter's moons. Before radio receivers, we were deaf to the electromagnetic spectrum beyond visible light. Each new instrument revealed phenomena that were always there but invisible to previous technology. Quantum sensors might reveal a quantum universe we currently can't perceive, and that universe might contain evidence of alien technology operating on quantum principles. The government's silence around quantum breakthroughs mirrors the silence around 3i Atlas anomalies. Both involve strategic considerations that override scientific transparency. Both involve capabilities that could provide decisive advantages to whoever develops them first. Both involve phenomena that challenge conventional understanding and require new frameworks to interpret properly. The pattern suggests we're living through a period where multiple frontiers are advancing simultaneously, each creating pressure for secrecy, each potentially connected to the others in ways we haven't recognized. Communication technology equals power, both in human societies and potentially in civilizations spanning star systems. Whoever controls communication controls coordination, enables collective action, can respond to threats or opportunities faster than rivals. If quantum communication represents the next frontier in this progression, nations will compete for dominance as fiercely as they competed for nuclear weapons or space capability. The fact that this competition is happening now alongside anomalies that might represent alien technology, creates a moment pregnant with possibility and danger in roughly equal measure. The question becomes whether we're ready to handle simultaneous paradigm shifts across multiple domains. Are we prepared for a world where quantum physics enables capabilities that seem magical, where AI surpasses human cognition in pattern recognition, where fusion provides limitless energy, where dark matter reveals the universe's hidden structure, where interstellar objects might be probes from alien civilizations? Each advance alone would be momentous. All of them together, concentrated in a few years, might represent a phase transition in human capability and understanding that we can barely imagine from our current vantage point. Part 15. The Cosmic Curtain. Call. Are we ready? October the 16th, 2025. That's the date historians might look back on as the moment when humanity could no longer pretend we're alone in the universe, or at least the moment when pretending became significantly harder. Avi Loeb published an image showing something that shouldn't exist, according to every model of comet behavior we've developed over centuries of observation. A jet pointing toward the sun, persistent across multiple exposures, visible in data that anyone with the technical knowledge could verify. This wasn't a rumor or a blurry photograph or an ambiguous signal. This was structured anomaly demanding explanation. Connect this to the broader catalogue of strangeness surrounding 3I Atlas. The nickel-dominated spectrum that suggests metallic composition inconsistent with typical comets. The low water fraction that violates expectations for icy bodies formed in the outer reaches of stellar systems. The extreme negative polarization placing this object outside the normal range of solar system objects. The trajectory that brought it close to the ecliptic plane when interstellar visitors should arrive from random directions in three-dimensional space. The coincidence with the WOW signal direction, that tantalizing burst of radio energy from 1977 that remains unexplained despite decades of follow-up searches. Each anomaly alone could be dismissed. Statistical flukes happen. Unusual but natural conditions can produce unexpected results. The universe is vast and strange, capable of surprising us with phenomena we haven't encountered before. But when anomalies accumulate, when multiple independent observations all suggest something isn't fitting our models, you reach a point where dismissal becomes harder than acceptance. The burden of proof shifts. Instead of demanding evidence that something extraordinary is happening, you start demanding evidence that something ordinary can explain all these oddities simultaneously. The institutional silence amplifies the mystery. Mars observations that showed nothing unusual, despite better viewing conditions than Earth-based telescopes. The Psyche probe blackout during exactly the period when it could have captured valuable data. The government shutdown that made scrutiny more difficult. The careful hedging in official statements, emphasizing caution and alternative explanations while avoiding direct engagement with the anomalies most people find compelling. This pattern of avoidance feels deliberate, whether it actually is or not. We're living through a convergence of frontiers unlike anything humanity has experienced before. Dark matter detection experiments showing stronger signals than previous searches hints that we might finally be on the verge of confirming the existence of particles that outweigh ordinary matter 5-1. Fusion power breakthroughs using AI-controlled plasma that achieve record energy gains, bringing us closer to the unlimited clean energy we've been promised for generations. Artificial intelligence discovering exoplanets in data humans analyzed but missed, demonstrating that machine learning can perceive patterns beyond human cognitive capabilities. Quantum communication satellites creating networks that could enable capabilities classical physics can't match. Each of these frontiers represents potential paradigm shift. Dark matter confirmation would revolutionize cosmology and particle physics, forcing us to acknowledge how little we understand about the universe's fundamental composition. Practical fusion would solve the energy crisis and enable space exploration on scales currently impossible. AI surpassing human pattern recognition might be the first step toward artificial general intelligence that can solve problems we can't even formulate properly. Quantum networks could enable communication and sensing beyond current limits. And then there's 3I Atlas, the anomaly that might represent contact even if it's not deliberate contact, even if it's just the residue of alien technology passing through our neighborhood, without noticing or caring about the apes on the third planet who are desperately trying to understand what they're seeing. The narrative here isn't about certainty, We don't have certainty. What we have are observations that don't fit, patterns that suggest something interesting is happening, and institutional responses that raise more questions than they answer. The scientific method requires skepticism and demands evidence before accepting extraordinary claims, but it also requires following evidence wherever it leads, even when it leads to conclusions that make us uncomfortable. Historical parallels teach us that humanity has faced these moments before. Galileo turned his telescope to the sky and saw moons orbiting Jupiter, direct evidence that not everything orbits Earth. The observation was simple, replicable, undeniable. Yet it challenged the geocentric worldview so profoundly that institutions resisted for decades. The evidence was always there. The barrier was psychological, not empirical. The atomic age began not with slow accumulation of knowledge, but with sudden breakthrough. Manhattan Project scientists achieving chain reaction and creating weapons that changed geopolitics forever. Suddenly, concepts that were theoretical curiosities became concrete capabilities with immediate strategic implications. The world divided into nuclear powers and everyone else, and that division shaped the next 80 years of history. The moon landing demonstrated human capability to leave our planet and survive in space, a psychological threshold as significant as the technical achievement. For the first time, humans looked back at Earth from another world and saw our planet as a small sphere in cosmic darkness. That perspective shift rippled through culture, environmental movements, philosophical thought about humanity's place in the universe. We might be approaching another such moment. 2025 remembered as the year when multiple paradigms shifted simultaneously. The year when fusion became practical, when AI surpassed human pattern recognition in meaningful ways, when quantum communication moved from laboratory to deployment, when dark matter hints became detections, when the evidence for alien technology became too strong to ignore even if it never became strong enough to prove definitively. The speculation about what this moment represents depends on how you weigh the evidence. If you're conservative, you see interesting anomalies requiring further study, but no reason to abandon conventional explanations yet. Natural processes we don't understand could account for 3i Atlas's behavior. The other frontiers are advancing normally without requiring any connection to each other or to questions about extraterrestrial intelligence. If you're more willing to entertain unconventional possibilities, you see a pattern suggesting we're being visited, have been visited, maybe are being visited routinely, and we're only now developing instruments sensitive enough to notice. The fusion breakthrough might be coincidence, or might reflect technological progress that makes us capable of recognizing advanced propulsion when we see it. The AI advances might be what finally allows us to perceive patterns our biology can't process. The quantum developments might reveal that we've been deaf to communication channels we didn't know existed. The truth probably lies somewhere between these extremes, as truth usually does. Some anomalies will resolve into natural phenomena we hadn't properly understood. Some might actually be evidence of alien technology, not necessarily active missions, but debris from the galactic engineering of civilizations millions of years old. The universe is old enough that even very rare civilizations should have left traces, waste products of industry or exploration, that drift between stars long after their creators disappeared. What matters isn't reaching immediate conclusion, but maintaining the willingness to investigate honestly. The failure mode here isn't being wrong about whether 3i Atlas is artificial. The failure mode is refusing to look seriously because you're afraid of being wrong, or because acknowledging anomalies threatens comfortable assumptions or career stability. Science advances through careful investigation of things that don't make sense, not through defending established models against uncomfortable data. Are we ready for contact, even passive contact through the discovery of alien artifacts, passing through our solar system? This question has no simple answer because humanity isn't monolithic. Some people have been ready their entire lives, consuming science fiction and SETI updates with the hope that we'll finally get confirmation we're not alone. Others would struggle with the revelation, religious frameworks or philosophical commitments challenged by evidence of alien intelligence. Most would probably shrug and go back to their lives after the initial excitement faded, because distant aliens have minimal impact on daily concerns about jobs and relationships and health. But the implications cascade through every domain. If we're not alone, then the universe is full of intelligence, which means the future involves either contact or isolation from neighbours we know exist but can't reach. If alien technology is passing through our solar system, then engineering capabilities exist far beyond anything we've achieved, which means the universe permits things we consider impossible. If we're being studied or observed, then our development is potentially important to others, which raises questions about interference or guidance or judgment we can't answer. The proof may already be here, not proof beyond doubt, but proof enough to shift probabilities significantly. The October 16th image, the accumulated anomalies, the institutional silence, the convergence of multiple frontiers all pointing toward conclusions we resist because they're too big to process comfortably. We're at a decision point. We can continue looking away, explaining away, dismissing those who take anomalies seriously. Or we can lean into the discomfort and investigate properly, accepting that investigation might lead to conclusions that change everything we thought we knew about our place in the cosmos. The cosmic curtain is lifting whether we're ready or not. The question is whether we have the courage to look at what's being revealed and the wisdom to respond appropriately. History will judge us not by whether we were right about 3i Atlas specifically, but by whether we were brave enough to follow evidence wherever it led, and honest enough to admit when our models failed to explain observations. The proof may be here. The question is, what will we do with it?